Today's theme will be radioactive minerals, which are the raw materials for our nuclear energy program. In this, we shall start with introduction, and in this we shall first see what father of India's nuclear program, Dr. Homi J. Bhabha, said. He said, for the full industrialization of underdeveloped areas, for continuation of our civilization and its future development, atomic energy is not merely an aid, it is an absolute necessity. This theme is in continuation of the previous lesson on coal and petroleum. All these resources come under the category of non-renewable resources. Of the four radioactive elements, uranium, thorium, rubidium and potassium, the former two are the backbone of nuclear power generation. Since the commissioning of nuclear reactors in the 1950s for power generation, nearly 24 countries have gone nuclear. PowerPoint 1 illustrates world electricity production and the share of nuclear contribution in it. The theme of radioactive minerals will be discussed under the following heads. We will begin with behavior of uranium and thorium, followed by important ore minerals of uranium and thorium. Then we will go to origin and classification of uranium deposit, followed by thorium deposits, and then we will come to rare earth and rare metals. As a generalization, uranium and thorium content of common rocks is not much. In granite, it is 4 and 15 ppm, while in basalt just 1 and 3 ppm. Shale has same amount as granite. In the average crust, these figures are 2 and 8 ppm respectively, as you will see in PowerPoint 1 and 2. However, natural refining processes have been at work to enrich these two radioactive elements to a workable deposit level. Behavior of uranium and thorium in the secondary environment is somewhat different. Both uranium and thorium are strongly oxyphile, that is oxygen loving. Therefore, in crustal rocks, their presence is never in a native but combined state. Uranium minerals in particular will occur as oxides, hydrated oxides, multiple oxides, silicates, carbonates, vanadates, phosphates, sulfates, arsenates. Uranium and thorium have strong affinity with molybdenum, barium, copper, iron, phosphorus and selenium. During magmatic stage, uranium remain in solution till the end stages of crystallization and will appear as disseminated grains in rocks or as vein type deposit along faults, fractures, shear zones, breccia zones and other openings. During sedimentary cycle, uranium and thorium may part their ways. Uranium is soluble easily and gets transported and reappears as chemical precipitates. Thorium has poor solubility and its minerals are fairly harder and durable. Thus, it has a tendency to occur as placer deposits, that is sedimentary cycle. In particular, as beach sands, while uranium is won both from its primary and secondary minerals, in common rocks types both prefer magmatic rocks that are both silica and alkali rich. Silica may be more than 62%. Both have strong association with hydrothermal sulfide deposits. In the secondary cycle, they have affinity with carbonaceous and phosphatic rocks, while during metamorphism they have preference for low grade, that is around 350 degrees centigrade rocks like phyllites and schists. It may appear strange, but both uranium and thorium are also characterized by their biophile tendency. Thus, they can also get concentrated in carbonaceous materials like humus, coal, petroleum and bitumen. Uranium and thorium during igneous processes go together along with other elements of the lanthanide series and rare metals including zirconium, hafnium, niobium, tantalum, beryllium, lithium and tin. Due to their similarity of ionic size, charge, electronegativity, uranium and thorium not only make their individual and combined minerals, but by substitution enter rare earths and rare metal minerals as well. Common chemical combinations in which uranium and thorium occur include oxides, that is uranites and pitchblende for uranium and thorianite, for the TH and U combined, hydrated oxides, multiple oxides, silicates mostly coffeonite and thorite, hydrated silicates and hydrous phosphates, that is monazite and xenotime. Hydrated phosphates, autunite and torbaronite, hydrated arsenates, hydrated vanadates, hydrated sulfates among are the important ones. 4 or 5 of the important minerals will be described briefly. Uraninite and pitchblende are the most common and best representatives of the uranium family and major ore mineral of uranium metal. Their composition is represented by uranium oxide, and uranite is isometric, occurring as octahedral crystals or massive in shades of black and brown with no cleavage, having conchoidal fracture, submetallic cluster. The hardness is around 5.5 and specific gravity between 8 and 9. Pitchblende is a somewhat impure variety occurring as cryptocrystalline or amorphous form, showing botryoidal habit. Color is black with a greenish tinge. Its hardness is around or less than 4, while specific gravity is less than 6.5. Uranium content in these two oxides of uranium may be up to 88%. Thorionite is a mixed oxide of uranium and thorium, up to 44% uranium and 88% thorium. It is black in color, isometric and nearly black in color and opaque. Hardness is 6.5 while specific gravity is 9. There is complete series between uraninite and thorionite. Among secondary uranium minerals, autunite, which is hydrated calcium uranium phosphate, and torbaronite, hydrated copper uranium phosphate, and carbonates, arsenates, sulfates strike out due to their bright and attractive colors in greens, yellow and reddish, as also due to their fluorescence. Their uranium content varies between 47 to 50%. All three geological processes steadily work on the average crustal abundance of these two elements and concentrate their level such that mining and extraction becomes possible and profitable. Among plutonic igneous rocks, granitoids, pegmatites are their favorable hosts, while rhyolites and acid tuffs among the volcanics. Hydrothermal activity enriches their level further. Sedimentary processes concentrate levels of uranium in rocks like sandstone, conglomerates, phosphatic and carbonaceous rocks like black shales. Low-grade metamorphic and metasomatic activity of shales also makes phyllites and shales and schists as hosts for uranium mineralization, particularly in structurally weak zones. International Atomic Energy Agency has given at least 15 classes of uranium deposits depending upon their economic significance and geological setting. Making it more simple, we can divide these 15 types into two broad categories. First, those formed by internal processes and the ones by secondary processes. Under the category 1, that is deposit formed by internal processes, we have hydrothermal veins, intrusive types, volcanics, metasomatite and metamorphite. In the second category, that is deposit formed by secondary processes, we have unconformity related, quartz pebble conglomerates, sandstone hosted, breccia complex, phosphorites, collapsed breccia type, surficial, lignite hosted, black shales and all the rest coming under the category of other types. Hydrothermal vein types at low temperature and low pressure are always the epigenetic type deposits occurring in fissures, fractures, breccias, talkworks, and uraninite and pitchblende are the main minerals. They were discovered prior to the Second World War and are considered the classical type of uranium deposits and have wide distribution in USA, Europe, Canada, Africa and even in India in Singhbhum shear zone area of Jharkhand and Gogoi in Karnataka. From world standards, our deposits are fairly low grade, ranging 0.035 to 0.65 U3O8 content and low tonnage. Intrusive types are characterized by large tonnage but lower grades in elaskites, peralkaline granites, carbonatites and cyanides. The ones in Namibia called the Rosing deposit, Palabora deposit of South Africa and Greenland are good example. Deposits of Russia and Ukraine come under the metasomite type and are associated with albitites and carbonate metasomites. Globally, sandstone type uranium deposits are widely distributed and mostly occur in Phanerozoic period. Several large deposits in USA like Colorado Plateau, Wyoming Basin, in Texas, in France, Russia, Australia and China have deposits of this type. Host sandstone and arkose derived from basements, granitites and acid tuffs are coarse and are interbedded with clays, mudstone and associated with carbonaceous materials and sulfides. Pitchblende and coffeonite are the common primary minerals. Mahadak sandstone of Cretaceous age in Meghalaya in northeast India is considered a medium tonnage deposit of this type. Neogene shivalics of Himachal Pradesh, Uttaranchal and Jammu and Kashmir have other prospects. Quartz pebble conglomerate types are generally found between the Archean basement and the overlying Proterozoic rocks. Witwatersrand of South Africa and Blind River conglomerates of Canada are the best examples. One of the largest tonnage polymetallic deposit, which contains 0.06% U3O8, is Brixia complex type. Olympic Dam deposit of southern Australia is the best example. Phosphorite types are to be found in USA and Morocco, and uranium from these is recovered as a byproduct with phosphoric acid manufacture. Black shales as uraniferous source are rather unique in that they demonstrate the dual capacity of uranium to behave like a biophile element too, though it is strongly an oxyphile element. Primary thorium minerals get concentrated in acid igneous rocks and metamorphic rocks of higher grade, generally granulite facies rocks. Thorionite containing up to 64% thorium and uranite are commonest oxides. Secondary thorium minerals include a supergene variety called thorogumite, which is hydrated thorium silicate. However, the best known source of thorium is mineral monazite, which is cerium, yttrium, lanthanum, thorium phosphate, and xenotium, yttrium phosphate. Both are anhydrous phosphates. A special word about monazite is in order. It is a rare earth phosphate. However, a monazite with no content of thorium is unheard of. It is the commercial source of rare earth in which appreciable amounts of rare earth elements are substituted by thorium and phosphorus by silicon. Thorium substitution can be so extensive that monazites may contain up to 26% thorium, thus making monazites the main source of thorium. Monazite crystals belong to monoclinic system. It is yellow to reddish brown in color, nearly translucent, having a resinous luster. Hardness lies between 5 to 5.5 and specific gravity between 4.9 to 5.5. Monazite is found as an accessory mineral in granites, applites, gneisses and pegmatites, but economic deposits are mostly found as detrital sand and gravels due to its being chemically resistant and heavier, along with other heavy minerals like zircon, magnetite, ilmenite, rutile, etc. For countries like India, which has reasonable monazite resources, thorium fueled reactors will have an edge over uranium fired reactors. In module 5 we shall see rare earth and rare metals. While uranium and thorium are the backbone of nuclear energy program, few other rare metals which we call simply RM, have also their specialized applications. Also, uranium and thorium are known to substitute these elements substantially. These includes rare metals like niobium, tantalum, beryllium, lithium, and the group of the rare earth elements lanthanum to lutetium in the periodic table, ranging from atomic number 57 to 71. There is yet another group of elements that enter application in nuclear technology. Together these are referred to as RMRE, and along with uranium and thorium come under the wing of Atomic Minerals Directorate for prospecting, mining and development. A very brief summary of RMRE is presented. Beryllium. Beryl is the only source for this important metal of nuclear technology. Pegmatites are its storehouse all over the world. In India, pegmatite belts of Bastar, Malkangiri in Orissa, Jharkhand and Rajasthan hold beryl resources. Beryllium is used as a canning material in nuclear reactors. The mineral for zirconium is zircon, which is a common accessory mineral in acid igneous rocks and as detrital grains in placer deposits like monazite sands of Kerala, Andhra and Orissa. Pure zirconium derived from is used as a covering material for atomic reactors as neutron absorber. Niobium alloy is used as pressure tubes in heavy water reactors. Tantalum is used in vacuum tubes and heat shields. Next, lithium. It is used in nuclear fission. Its main source is lithium mica called lepidolite and spodumene, which is a pyroxene. Lepidolite occurs in pegmatites along with topaz and tourmaline. Uranium and thorium, members of the actinide series, are the two important radio elements which are the main contributors for the production of nuclear energy. Average crustal abundance of thorium is 8 ppm, is more than that of uranium, which is just 2 ppm. Both have strongly oxyphile characters, thus they do not occur in native state, but only as oxides, silicates and other chemical combinations. Both prefer magmatic rocks that are rich in silica as well as alkalis. Of recent, as a source of atomic energy, thorium is receiving considerable attention. For countries like India, which does not have sufficient uranium resources of its own, but reasonable monazite resources, thorium fueled reactors will have an edge over uranium fired reactors in our energy production scenario.